And so we're very happy to have Pau Figueras from Queen Mary University of London, who's going to tell us about higher derivative theories of gravity. Thank you.
Well, first of all, I want to thank the organizers for inviting me, and just to warn the audience, this is a physics talk, so don't expect estimates or proofs of theorems or anything like that. And if there's anything which is unclear and not too outrageous, just feel free to ask. Okay, so today I'm going to talk about some work that I've been doing in the past few years about how to basically formulate the initial value problem for a large class of higher derivative theories of gravity. So we're talking about theories with higher than second order equations of motion. So the question is how one can formulate the initial value problem for these theories and extract their predictions in a way which is consistent and meaningful. Why is this not working? Okay, so I should start with some motivations, and from a physics side, then the main motivation driving research in this area is the fact that now we live in the era of gravitational wave astronomy, and the fact that one can now detect gravitational waves produced in mergers of black holes, and therefore in the strong field regime of the theory offers the opportunity to perform new tests of general relativity and trying to figure out if what else there is out there. And in performing these tests, one hopes to sort of, as I said, just understand the actual nature of gravity at the more fundamental level. But as I hope I'll convince you in this talk, then there's also some interest from the mathematics point of view to understand the classes of theories that naturally emerge in this context. So in the case of theories of gravity, the difficulties in carrying out this program are those that you see in here. So first of all is that at the moment, most tests of that are done with gravitational waves assume GR. So one compares observations with GR. So we don't know whether there is a theory out there which provides a better fit to the data. And for that, one needs to be able to extract predictions for these alternative theories of gravity that people have come up with. And one of the problems in doing so is that there is not just one preferred alternative theory of gravity, because there's some observational evidence or some theoretical preference, whatever. There are like hundreds, right? So if you go out there, then you'll be quite amazed about how creative people can be. And of course, they have different degrees of motivation or whatever, but there is not a single theory that one should focus the effort on. And related to this is you have this bunch of theories. So the question is, as I said, how can one extract the predictions for these theories, say for black hole binaries, and then compute from first principles from these theories what the waveforms should look like? And this question basically boils down to the question of whether these theories have a well-posed initial value problem. So that's what we are going to address here. So effective field theory provides a framework in which one can treat all or large classes of these theories in a way which allows one to parameterize the deviations from GR in a way that one can treat also the strong field regime of the theory. And the idea behind effective field theory is that effective field theories, what they do is they parameterize the effects of unknown physics at very short distances that you do not understand. This could be quantum gravity or something else. The effects of these unknown physics at very short distances at the sort of large scales that one can probe with current experiments. And the basic ingredients of effective field theories, at least from a bottom-up perspective, are those that are listed here. So first of all, one needs to identify what are the degrees of freedom that one can probe with low energies or large distances. And in the case of gravitational theory, this would be, say, the metric, the space-time metric. But there might be some other light fields, could be like scalar fields or gauge fields. So one has to identify the active degrees of freedom at these long distances. Then one can also has to then identify what are the relevant symmetries at the scales that we are probing. And then with these two ingredients, one then constructs all possible interactions amongst these low energy degrees of freedom. And then you need another ingredient, namely a power counting scheme that allows one to weigh these different interactions. And the natural one to use is derivatives of these low energy fields, because all these interactions, so that you put them in an action, and therefore the dimensions have to match. So they will all come with some suitable powers of a typical length scale that will tell you when these new degrees of freedom that you're ignoring become important. And you will be comparing the sort of scale of variation of your low energy degrees of freedom to the scale at which these new physics should appear. And you want these two scales to be large, to be separated, so that it makes sense to come up with an expansion. Okay, so that's the basic ingredients. Of course, if you know the full UV theory, and we'll see an example of this, then one can come up with a suitable one can take a suitable low energy limit of this UV theory, so that you are left with only the low energy degrees of freedom with a bunch of interactions amongst them. But as I said, one can do that only consistently if you happen to know and be able to solve the full UV theory, which is rarely the case. So that's why we typically take this bottom-up approach. And these various interactions will come with some unknown coefficients, which, again, if you knew how to solve the fundamental theory, you could compute them in principle, and there are cases in which you can't do that. But in general, these are what you then constrain or measure in experiments. So as I said, with these three ingredients, you construct the low energy effective action as an expansion in derivatives of the low energy fields, and with some dimensionless coefficients, which carry information about the UV theory. So if you can measure those or you can constrain those, then you can learn some non-trivial information about the UV theory. And that's the program that we want to carry out. So in these expansions are not unique. There's some redundancies, because you can redefine your fields by just perturbatively in a derivative expansion by the equations of motion, and then you obtain physically equivalent theories, but they have different expansions. But at the level of the predictions at a certain, say, distances, then they are equivalent. And as I said, the coefficients, these are what you want to measure in experiments, you want to constrain. But if you impose that the fundamental theory has some properties, like, for example, that it's local, it's a unitary, say, quantum field theory, or it's Lorentz invariant, or whatever, then one can put constraints on these coefficients. So, said in other words, so if you can measure those or you can constrain those, then you can learn some non-trivial information about what the UV theory, the fundamental theory, would be. And if we could do this with gravity, of course, we would be able to learn something about quantum gravity, which is something that people have been trying to do for a long time. And we are interested in situations where there's a large separations of scales, and that's typically what you should expect on theoretical grounds in gravitational theories, because, say, the scale of, say, quantum gravity is a Planck scale, or maybe lower if you have string theory, so that you have another length scale, the length, say, of strings. So it could be a bit lower than say, Planck scale. But we'll be comparing a very short distance to, say, macroscopic black holes, right? With, I don't know, for stellar mass, for solar mass black holes, we're talking about objects whose size is in kilometers, right? And we're comparing this to very small distances, which is where you expect quantum effects to be important. So we're in a situation in which there's a large separation of scales. So then in experiments, obviously you will not be sensitive to all the coefficients in the series. So it makes sense to truncate these series to just keeping only the first few terms, because these are the only ones you can ever hope to measure or constrain. So we'll be talking about higher derivative theories of gravity that we have truncated at a certain order in this derivative expansion. And now we want to make sense of these theories. So that's what we want to do. So typical theories that have a reason in the community in this context is scalar tensor theories of gravity. And if you carry out this program of just identifying the low energy degrees of freedom, in this case will be the metric and a scalar field, and you construct all possible interactions at the 4 derivative level, up to 4 derivatives, this is what you come up with after you've performed these field redefinitions. Right, so in the first line, you have the Einstein scalar field model, and in the second line, you have the higher derivative interactions. And these functions that can depend on the scalar field, but not on its derivatives, and this is what you want to determine and constrain with experiments, okay? And this is just a dual Riemann. So these two terms, they preserve parity but this term, because you've got the dual Riemann, this breaks parity. So if you say that your low energy theory should be parity symmetric, then this term would be forbidden. And then you only get these two terms, which are, this is a Lovelock term, that's a Hordensky-like term, so this will give you second order equations of motion, but non-quasi-linear equations. So that's why this theory has attracted interest in the community, because you get higher derivative type terms, but two derivative equations of motion. So these are easier to study. But most tests of GR are done with just vacuum gravity. So in vacuum gravity, if you carry out this program of constructing all possible interactions in a derivative expansion, up to 8 derivatives, this is what you come up with. So at the 6th derivative level, there are 2 cubic terms with 6 derivatives, one which is parity symmetric, one which is which breaks parity. So again, if you impose parity symmetry, then this term is not allowed. And then at the 8 derivative levels, then you have these 3 possible terms. So for example, if from a more fundamental theory of gravity, such as string theory, if you compactify to low energies, then all supersymmetric compactifications of string theory do not allow for this cubic term. So you only get 8 derivatives and above from string theory if you assume supersymmetry. So if you were to measure, say, the coefficient, this term, then you could say, well, at least at low energies, you have something which is non-supersymmetric compactification of string theory. So that would be something quite relevant in terms of learning something important about the fundamental theory of gravity. Okay, and for every particular compactification of string theory, if you take a suitable low energy limit, then you get precise numbers for this, which carry the details of this compactification. Okay, and this is very similar to what people do in hydrodynamics, because after all, hydrodynamics is the other paradigmatic classical effective field theory of the near equilibrium dynamics of fluid. And in the case of relativistic viscous fluid with conformal symmetry, and I picked conformal symmetry because it's more symmetry, so there are fewer terms that you can write down that are compatible with the symmetry. Then at the 0 derivative level, then you've got an ideal fluid which has no derivatives of the thermodynamic fields, namely the fall velocity and the energy density, and all dissipative effects are encoded in this object, which is written in a derivative expansion. So the first term you have is the shear tensor, has 1 derivative of the velocity, and at the 2 derivative levels, you have all these possible terms which are compatible with conformal symmetry. And for example, if you can solve the microscopic theory, then you can compute these coefficients. So for holographic fluids, like n equals 4 super Yang-Mills, then you can compute all these coefficients. But in general, you don't, and you just, this is what you fit in experiments. You may do simulations, trying to fit simulation to the data, and then you can then obtain these coefficients. So that's what we want to do with gravitational waves. But I just want to emphasize that the problems that one faces in gravity are the same that problems that people have addressed in relativistic viscous hydrodynamics, for instance. So in these truncated effective field theories that I showed you, one of the issues that one has is that the equations of motion are typically higher than second order in derivatives of your fields, except for Lovelock and Hordensky theories, but these are kind of exceptional because the derivative structure is very particular. So the question is how do you formulate the initial value problem? Because there's no, to the best of my knowledge, there's no general classification of PDEs which are higher than second order. So how do you even talk about well-posedness? But typically, at least in the usual setting, then the well-posedness of your PDE is sensitive to the highest derivatives of your PDE. But in this context of effective field theories, we are doing a derivative expansion. So in terms of the physical effects, then the highest derivative should be the least important ones. So there seems to be some tension here between well-posedness and the relevance of these terms from the point of view of effective field theory. And another related issue for these higher than second order equations of motion is that one needs to specify more initial data because they have more degrees of freedom. So another open problem is how do you do that? How do you do that in a way that is consistent with this derivative expansion? And because you have higher than second time derivatives, then there's a general theorem proven a long time ago by Strogatsky that you'll have ghost-like solutions that exhibit a runaway behavior, and they are unphysical because they're just a result of having truncated the series at some finite order. So how do you control them? How do you prevent those solutions from arising? So these are the basic problems that we will address. Now, of course, trying to, and as I said, these problems have arisen before in the context of relativistic viscous hydrodynamics and in other situations as well. So people have come up with solutions. And one possible solution is to do perturbation theory. You just linearize and you solve for each derivative in this perturbative expansion. And in that case, there's no issues with well-posedness because every term in the expansion of your solution then obeys, say, the second order wave equation or your second order equation with some sources which depend on the lower orders. So in this case, there's no issues with well-posedness, but the problem is that typically these solutions will have secular behavior. So these solutions will only be valid for a very short period of time, and that's clearly not optimal for if you want to do gravitational waves, we expect the two black holes to be orbiting around each other for a very long time. And you will also miss non-perturbative effects. Another possibility is to do reduction of order, which is to recursively use the equations of motion to solve for the higher time derivatives in terms of the lower special derivatives. And that's fine, but that's clearly breaks covariance. So if you have a relativistic system, that's really not an option. And another option that has been explored is the so-called fixing of the equations. So in that case, one packs the higher derivatives in terms of new objects, and one prescribes suitable equations of motion for this object. And this has been applied very successfully in relativistic viscous hydrodynamics, and under suitable assumptions, Figueras proved that in the regime in which hydrodynamics is applicable, then this way of dealing with the problems is actually sound, and it captures the right, say, long distance physics of interest. But we don't have a similar kind of statement in gravity, and the cases that have been attempted also are not covariant and have issues with, say, the Bianchi identities and so on and so forth. So what I'm going to talk about today is our recent proposal that we called regularization. So I hope it will become clear why we call it like that. So to motivate this, I'll just remind you, I'll just make two observations. I said earlier that when you do this expansion of the low energy effective action, one can do perturbative field redefinitions of your sort of low energy degrees of freedom by just removing certain terms in the expansion, right? Because they are just proportional to the lower order equations of motion, so they are suppressed on shell. And the theories that you obtain in this way are physically equivalent. On solutions, they give you describe the same physics. And as I said earlier, when it comes to well-posedness, what matters the most are the highest derivative terms. But from the point of view of effective field theory, those terms are the least important ones, because derivatives, we are assuming that derivatives that have the higher derivatives, the highest the derivative, the smaller it is in a suitable norm. Okay. So our idea was to exploit these two observations, and instead of performing field redefinitions to remove certain terms in this low energy action, so we perform perturbative field redefinitions which are proportional to the zeroth order equations of motion, which we assume to be well posed. And in doing so, we add new higher derivative terms to the action and therefore to equations of motion. But the terms that we add are very special. They're not just random higher derivative terms. They are terms that, because they are proportional to the zeroth order equations of motion and their derivatives, they inherit the nice high frequency behavior of the zero order equations, which is what you needed to show well-posedness for the theory. Okay? And because these terms that we add are proportional to the equations of motion on shell, they do not affect the original theory on shell. So they will provide physically equivalent solutions from the point of view of effective field theory. And moreover, the equations that we obtain will have a nice high frequency behavior and will allow us to show well-posedness. So the equations that you get, they're higher derivatives, so they're only weakly hyperbolic. And to establish well-posedness, it means you need to control the highest derivatives and some of the lower derivatives as well. But because we've performed this field with definitions, we obtain also the right structure for the lower derivative terms that allows us to still show that we have a well-posed initial value problem. And one thing that one must bear in mind is the question of the initial data, that one cannot just construct random initial data for this theory that solves the would-be constraints that you get, but you need to make sure that the initial data you construct for these extra degrees of freedom that you have then is compatible with this effective field theory expansion. Otherwise, you will get runaway solutions because you do not kill the ghosts. The ghosts are still there, but if you construct initial data, which is, as we'll explain, then there will not be a problem. Okay. I should say that a similar approach was also carried out in the context of relativistic viscous hydrodynamics, and this is known under BDNK. So it's very related ways of dealing with these equations. Because as I said, gravity and hydrodynamics are just classical effective field theories. So it's not surprising that similar approaches work for both. Okay, so I will try to make this more concrete in the case of a simple scalar field model, because one can do everything. And then I'll explain how one goes about carrying out this program for theories of gravity. So are there any questions so far? Okay, so if not, then let me just continue. So as I said, we'll implement this program in the context of the classical abelian-Higgs model. And the reason why we choose this model is because we'll take this as a UV theory, and then we'll take a suitable low energy limit. So we'll obtain this derivative expansion. And because here we know the UV theory and we can solve it, then we can compare how well our sort of EFT does compared to the full solution in a suitable regime where this comparison makes sense. Okay. And also this theory has been looked at by, as a toy problem for these kind of issues. So it's good to compare with what other people have done. Okay, so this has a global U1 symmetry, and you have this kind of Mexican hat type potential, and the vacuum breaks this symmetry spontaneously. And around this vacuum, you have 2 degrees of freedom, one which is a massive mode and one which is a massless Goldstone boson, right? And you can make this explicit by just writing your complex scalar field in terms of these variables there. So the massive field is this rho, and the massless field is basically the angle around the bottom of the potential. And in terms of these variables, then the equations, the classical equations of motion, as I said, this one's written here. So you've got this massive mode with some interactions and this massless mode. Okay, so this is the UV theory. And I should say that everything I'm going to talk about is classical. So we're just solving PDEs. So nothing is quantum here. So in fact, this theory has been looked at by these people, and they even prove global existence of solutions to this system. So that's our UV theory. Okay. Now, when this mass of this massive mode is large enough compared to the typical energies associated to your fields, and that translates into suitable boundedness assumptions on the derivatives of this field, one can integrate out this massive field. And this can be made rigorous and by these authors there. And one can derive the low energy effective action for this massless field. So you start with a massless, the typical kinetic term for a massless field, plus all these derivative self-interactions, which are just encode the influence, the interaction with this massive field into the massless field, right? But now here you've integrated the massive field, so you only get the massless field, okay? So here, because we obtain this theory from the UV theory, carrying out this integrating out procedure, which is described rigorously by these authors there, then these coefficients come with precise numbers. So if we were to do the same thing from the bottom-up approach, then we would have come up with the same terms with this sort of mass there, which you needed for dimension, so that the dimensions match. But then these numerical coefficients would be just some unknown coefficients, which are order 1. In this case, because we obtained this from a UV theory, then we know the precise values of this coefficient. But the fact that they are -0.5 and 2 does not matter for what I'm going to talk about. Okay. So we'll take this as our toy low energy effective action, and you vary this action, you obtain these equations of motion. And just to make it more explicit, so you can see that these are fourth order in derivatives, right? So now this is our problem. We want to construct solutions to this fourth order PDE such that they are compatible with this expansion in derivatives of this field theta. Okay, this is our task. Okay, so how do we do that? So in our approach, the segment makes field redefinitions proportional to the 0th order equations of motion. So this is just the second order equation. So this E2 is this piece there. Okay, so that's if you truncate this to this to the first term, and by doing this field redefinition and plugging into the action, then that's a new theory obtained, and as insist, because these and the previous one are related by this perturbative field redefinition. They describe the same physical phenomena. And now what we've achieved with this field redefinition is that we have these 2 extra terms into the action, which are just derivatives of the 0th order equation, which is box theta equals 0, so that we just take some higher derivatives. So now we vary this action, and we obtain the same equations of motion that we had before, plus these 2 extra pieces. So we started with a theory with a 4th order equation, and now we come up with a theory which has a 6th order equation. So, so I think that this is not ideal. It seems to have we have only made the problem worse, but I will argue that that's not quite the case, and I will show you now how to construct solutions to these equations, which are therefore solutions to the original problem. So to understand how to proceed is useful to look at the linear problem. Okay, so the linear problem is a 6th order PDE. So how do we solve it? It's linear, so one should be able to do it. So one can rewrite this equation in this suggestive form, where these m plus and minus are just parameters, which depend on the parameters that we introduced in our field redefinition. So we can choose them to be whatever they want. We are free to choose these parameters. But once you write it in this way, then it becomes clearer, perhaps, how to proceed. So if you now introduce a new field, which I call this theta 01 as box of theta, then the equation we have up there just reduces now to a 4th order equation. So now we repeat the problem, we repeat this again, and we now define this bit in terms of a new field. And now the original equation just becomes a massive wave equation for this new field. So just putting everything together, we traded a 6th order equation for our field theta as a diagonal system of wave equations for the original low energy field theta plus 2 extra fields, which are massive fields, and these are their mass parameters. So this is clearly well-posed, symmetric hyperbolic, and if one wants to construct bounded solutions to the system, then there's a hope to do that. But for that, all you need to impose is that these masses squared, are positive, right? Otherwise, you will be tachyonic solutions. And these masses that we have written over there, they depend on these parameters that we are free to choose. And as long as you choose them in these ranges, then you ensure that these masses squared are positive. So clearly, one can now construct solutions which are bounded for this linear system. So now we can just extend these to the full nonlinear problem, and we introduce the same definitions that we had before, plus some extra ones, which basically just encode derivatives of our fields. And in terms of these variables, then one can write down the original 6th-order equation in terms of a bunch of wave equations for these fields. And on the right-hand side, you have only lower derivative terms. So now you have a diagonal system of wave equations for massless and massive modes. So these terms over there, they are not degrees of freedom, they're just fully constrained, and these equations are simply just the propagation of these constraints. So they do not carry new degrees of freedom. So this system has 3 degrees of freedom, the original massless field theta, and 2 massive modes, which is this one here and this one there. So just to summarize, we obtain now, in this way, we obtain a diagonal system of wave equations, so symmetric hyperbolic, so well posed. The degrees of freedom, we have our low energy field, theta, and 2 massive modes. The masses are of the order of the mass of the UV field. And in order to have some hope to construct bounded solutions to the system, we need to ensure that these masses squared are positive, but we can always achieve this because they depend on the free parameters that we can choose. Now, it turns out that these fields are ghosts. So by this, what I mean is that because we obtain, for this particular theory, because we obtain them from a diffeomorphism invariant action, one can obtain an energy. So in the energy of the theory, the terms associated to this field are not positive definite. So in principle, the Hamiltonian is not bounded from below. So that could be a concern. And I'll explain that if you choose the initial data wisely and compatible with this expansion in derivatives, then this will not be a problem. So, any questions so far? Okay. So, of course, I'm not going to prove any theorems on this, but we can do some numerics, which hopefully will be convincing enough that what we do is sensible. Okay, so now we'll go to the question of the initial data. So here we have more degrees of freedom, so we need more data. So what do we mean by these more precisely? So remember, one of the fields that we introduced is just basically the box of our original field. So if you expand it, then it means that in order to provide data for this field, then we need to know the second time derivative of our low energy field. So how do we prescribe this data? And if you just give it some random value, then most likely you will excite the ghost fields and you'll get these runaway solutions. So this will just be signaling the breakdown of these expansion in derivatives. So intuitively, when you do this effective field theory, the only really degree of freedom that you have at low energies is this field. So intuitively, one should be able to prescribe data for these higher derivatives in terms of the only free data that you have at low energies, which is just the value of the field and its time derivative on your initial data surface. So the way to do it is to basically impose the equations of motion on your initial data surface and by doing that, then compute the time derivatives, the higher time derivatives that you need in an expansion in terms of this mass parameter. So just to see this explicitly, so if we just consider the theory truncated at the quartic order, just because the equations are shorter and it's easy to show how it works, but it's the same for the 6th derivative theory that I showed earlier. So we would impose the equation of motion at time 0, and by imposing, we can now solve this equation for the second time derivative of this field in terms of the values of the field and its spatial derivatives on the initial data surface, which we know, and likewise for the time derivative. So we can, of course, we know this on the initial data surface, so we can take further derivatives. So in this way, we can obtain the value of the second time derivative of our field in terms of our free data and its spatial derivatives. And you can do that for the higher time derivatives that you need as well. And one may worry that because we are imposing this equation on a particular slice, then this might break covariance. But it was actually shown by these authors that covariance is preserved, at least within the era of the effective field theory. So the loss of covariance is higher order in the 1/m expansion. So that's what this means. And one can generalize this procedure to gravitational theories as well. Okay, and that's we'll argue that if you construct initial data in this way, which is compatible with the derivative expansion, then the fact that you've got fields which are ghosts is not a problem. So as an example, we put ourselves in the worst possible situation. We just consider this theory in 1+1 dimension. So in this case, there is no decay or anything that can help us. And furthermore, we'll choose a domain with size 2 and periodic boundary conditions. So again, it's just the worst possible case you can imagine, because there's no decay, nothing. And we'll choose a mass scale 100. So in some sense, you want your derivatives of the fields to be small compared to 100. Okay, and one could argue that this is on the borderline of being acceptable. And okay, one can solve the UV theory, and the UV theory doesn't care. So the UV theory can, as long as you provide suitable data for the fields, then you can just solve it. It doesn't care about the separation of scales or anything. And if you choose initial data for which it makes sense to have this expansion in derivatives, this is the solution that you get. And for this data, even though this is the solution to the UV theory, then the solutions to the effective field theory that I showed earlier cannot be distinguished by the naked eye with this one. And you can do a more precise studies of what the error is, and you can show that it decays as a suitable power of 1/m. But more interestingly, one can look at these fields. So this field is basically the box of our low energy field. And you can see that it remains bounded for long times. And that's basically box squared. And again, you can see that it remains bounded at late times. As I said, one can do a detailed study of how the errors in DFT compare with the UV theory, and you can see that they scale with a suitable power of 1/m. So one concludes that this provides a consistent solution to the effective field theory. And just to insist on the point of initial data, so one has to choose initial data for which it makes sense to do this derivative expansion. So if you do a spectral decomposition of the UV solution, then most of the weight should be at small frequencies. This is what it means for the solution to be expandable in derivatives. And you can see that UV solution, basically most of the weight is at very small frequencies. And for the solution that we obtained with the effective field theory, then the same is true. And this is basically showing that you do not excite the ghost fields, because if you excite the ghost fields, these encode the higher derivatives. So in that case, you would see that the weight should be in the sort of high frequencies. But this doesn't happen here. And these peaks that you see here, this is just at the values of the masses of this ghost field. Okay, but the important thing is that the solution is in the low frequency regime, and that's where it makes sense to expand in derivatives. So what happens when things go wrong? So to see this, it's easier to illustrate it in the case of the theory truncated at this order. And the reason is that, as I said, in this case, this is a Hordensky theory. So you don't need any of this fancy stuff to solve it. And you can just, the equations of motion you derive from varying this action are just given here. And they are second order in derivatives, but they're not, they're second order in derivatives. And this is just a wave equation. But now the metric controlling the propagation of this field is not the spacetime metric, but is some effective metric, which depends on the field and its derivatives, just like in fluids. So in this case, one can have one can have shocks from studying from smooth initial data, which is something you don't have typically. And the issue with this, you can construct solutions. The initial value problem is well posed for as long as this effective metric is Lorentzian. And this happens when the derivatives of this field are suitably small compared to this mass scale. Okay, so in the weakly coupled regime, on the EFT regime, then this theory is well posed and you can just solve it. But one can do the same thing with this regularization. And if you do that for this theory, again, that's what you get. That's the same field that we had earlier. And now we have a massive field, which is basically the box of the original field, and some auxiliary field, which is just one derivative of the scalar field. So we've turned the problem into just a bunch of wave equations, two massless fields, one massive field, and some lower order terms. So it's clearly hyperbolic. And now the propagation of all modes is controlled by the space-time metric. So in this case, there's no issues with the metric not being hyperbolic or whatever, but we'll see that there are other issues. So yeah, so in this case, I should say that the only thing you need to worry about is that you need to make sure that this coefficient is negative, so that the mass squared is positive of this field. So that's the only restriction you have. So what happens now if you choose initial data for which the derivatives of the field are not small, but are of the order of the cutoff scale? So first of all, if you solve the UV theory, then this is the dashed black line, nothing happens, right? The UV theory does not care about this separation of scales or whatever, and it's, you can just solve it. For the first effective field theory that I showed, the one that you did not have to do this regularization and so on, what happens is at some point, this metric ceases to be hyperbolic, so you cannot continue the evolution any further. So your system is no longer well posed. So this evolution stops. And for the regularized theory, what happens is that even though the mass squared of this field is positive, then the interactions contribute to the effective mass. And when this condition is, when your initial data satisfies that condition, then the effective mass can become tachyonic, and then this field starts growing. So this is a ghost. This is the behavior you'd expect from a ghost. So that's a runaway solution. And this is just, in this case, the box of the theory of your field. So it means that the higher derivatives are becoming important. So effective field theory breaks down. So, so that's the end of it. So in any numerical simulation, then at some point, very soon, your code would crash. So what I'm trying to say is that both EFTs break down pretty much at the same time, in fact, but they break down in different ways. And the breakdown is just related to the fact that you are pushing the EFT beyond its regime of validity. So why these ghosts are not a problem if you choose initial data wisely in the way that I described. So for this particular scalar field theory, the model equation for the ghost is this massive wave equation with a cubic term. So that corresponds to having a quartic potential with a suitable sign of the coupling constant. So this is basically a field obeying a wave equation with this inverted potential. So that's this potential is unbounded from below. So that's what I said earlier. The Hamiltonian is unbounded from below. So in principle, this field can become arbitrarily negative. So that's the runaway solution. But it turns out that even without the mass term, so you would have like basically a field sitting at the top of this inverted potential, then for suitably small initial data, one can construct global solutions. And in 3+1 dimensions, because in 3+1 dimensions, you have dispersion that prevents the field from just rolling down. In the case of a mass term and for quadratic interactions, then the situation is even better. Because then basically what happens is that your field sits there, and the fact that the potential is, is unbounded, as long as your data is suitably small, which means that your field will remain at the bottom of this potential and nothing bad will happen. So this can be made rigorous. So that's basically how one treats the ghost fields in this context. And the prescription that I explained earlier about the initial data basically just allows you to construct initial data at the bottom of this potential. So then you can expect to be able to construct global solutions to these theories. And the fact that you have ghosts is really not a problem. Any questions so far before I move on to the very last part? Okay. So now we are going to apply these to higher derivative theories of gravity, which is what we were originally motivated by. So in our paper, we proved the following theorem. So if you have a higher derivative theory of gravity, we start with this Einstein-Hilbert term, and we ignore the cosmological constant term because we're interested in just the dynamics of isolated objects like black holes. You have a truncated high derivative theory of gravity. So here you can have any sort of polynomial of curvature, which include parity violating terms in particular, and you truncate it to a certain order. And we showed that you can always make a field redefinition proportional to the to the zeroth order equations of motion. So to this original Lagrangian, you add a bunch of terms of this form, where this is just the Ricci tensor, and this is the Einstein tensor, constructed from the spacetime metric. And the number of terms that you add depends on how many derivatives you have in your original theory. Okay? And if you do that, then the new regularized theory, which is this Lagrangian plus this one, is physically equivalent to the original one, just involves this perturbative redefinition. And you can show that in this case, you can just write down the equations of motion as a bunch of wave equations for the metric and some new degrees of freedom, which are basically just the Ricci tensor. And the rest are auxiliary fields, which you can also obtain wave equations for just using the Bianchi identities. So we'll see this more explicitly for the scalar tensor theory of gravity that I showed earlier. So this is just the same theory I wrote down at the beginning of the talk. And if you vary this action, the equations of motion are third order in derivatives, and the third order derivatives come from this term. Okay, that's the term. And if you throw away these two terms, then as I said, this violates parity, and this is known as dynamical Chen-Simons theory, which some people happen to find interesting. Okay, but here I'm interested in sort of trying to make sense of it and solving it in a way that is consistent. Okay, and if you can compute waveforms and rule it out, then that will be a plus. Okay, so how do you go about? In this case, you do a field redefinition proportional to the zeroth order equations of motion, and if you do that, then you augment the original theory by a bunch of new terms. The structure is really not important, just to say that you seem to have made the problem worse than what it was, but actually you've made it better. And the way to see how you made it better is that now the equations of motion that you obtain for the new theory have this form. So that's the left-hand side is very suggestive. And the right-hand side, the derivative structure that you get is just summarized in there. You have first and second derivatives of the scalar field, have the Ricci tensor and the Weil tensor. And for the equations of motion for the metric, you have the structure on the left-hand side, this box of Ricci plus a mass term. And on the right-hand side, you have up to a term which has a derivative of the Ricci. So that's the third derivative that I said you have earlier. I mean, the precise equations are really not very illustrative, but that's the derivative structure of the equations of motion that you get. And we do the same thing as in the scalar field problem. So we introduce new variables, one that absorbs a derivative of the scalar field, and one that's basically the zeroth order equation of motion for the scalar field. We now promote this to a new variable. Then the structure of the equations suggests that we should promote the Ricci tensor to a new variable. And then we also introduce, so this is the variable that we have here. This is a variable, we promote this to a new variable. That's just absorbs the derivative. So just as in the scalar field problem, this is just a constraint. It will not carry any new information. And for the Weil tensor, we just decompose it into electric and magnetic parts. But again, you can determine, if you know the spacetime metric, you know the Weil tensor. So intuitively, these play the same role as these variables. We just absorb some derivatives that will then allow you to write the system as just a bunch of wave equations. So they will not carry, they are not new degrees of freedom. Because, I mean, as I said, intuitively, if you know the spacetime metric, you know the Weil tensor. So if you do that, then the equations of motion for this scalar tensor theory written here. So you've got now the Einstein equations for the spacetime metric. And now I say you promote this to a new variable, the Ricci. So now the right-hand side is our dynamical variable, which is the Ricci. So if you write if you use generalized harmonic coordinates, that's a wave equation for the metric with some source, which is this tensor. So for the scalar field, we have just the definition I introduced earlier. For the derivative of the scalar field, you just hit it with a wave equation, and you get that, and that's just the propagation of the constraint that I showed earlier. And now this is the scalar equation of motion. And now on the right-hand side, you have some non-trivial function, but depends only up to now derivatives of the scalar field. Now these terms have no derivatives, and these are now we have no derivatives because we've promoted those to new variables. Now the equation of motion for the metric now takes similar structure. So it's now a massive wave equation for our new variable, which has a scalar and a tensor degree of freedom. And then the right-hand sides just again have lower derivative terms. And then we evolve the Weil tensor using just the Bianchi identities, which are also strongly hyperbolic. So in this case, you close the system, and it's now symmetric hyperbolic, so you can just go and solve it. Okay, and you would then construct initial data in the way that I explained just for the scalar field, but just applying it to this theory. So the degrees of freedom that we have is just the metric and the scalar field, and now we have this term and the Weil tensor, and the Ricci tensor, which has a scalar degree of freedom and a tensor degree of freedom, and the rest are just auxiliary variables, which are fully constrained, so they're not new degrees of freedom. So all we need to do to impose to hope to find bounded solutions is that the masses of these fields are masses squared are positive, but in this case, the only constraint we have is that these constants that we are free to choose, they should be negative. But other than that, then that's it. So for those of you sitting there that sort of have been proving like stability of Minkowski space in different gauges and so on and so forth, now perhaps something else that could be interesting to do is to, instead of just trying another gauge, which is generalization of whatever, then you might want to sort of try to prove stability of Minkowski space in these higher derivative theories of gravity, which if you write these out, just a bunch of wave equations, so that might be also interesting, shall I say. So there's no shortage of stabilities of Minkowski that remain to be proven. Okay, so it's very nice to show that you can formulate this as a bunch of wave equations. But it's even nicer if you can actually solve them in some physical situations. So that's something we are still work in progress. And one thing we've tried is for the dynamical Chern-Simons theory, the one with third-order equations of motion. One can just evolve a single black hole space-time. And if you choose a coupling which is constant, then you see that the black hole develops scalar hair. So that's the L2 norm of the scalar field on the horizon of the apparent horizon of the black hole, including full back reaction and everything. So it develops just a hair. But if you look at the profile of the scalar field on the horizon, then this is the polar angle on the horizon 2 sphere, and that's the azimuthal angle. And you can see that the scalar field breaks parity because it has one sign on the sort of upper half of the equator and a different sign on the lower half of the equation. So it shows explicitly that here you are breaking parity as that term promised to do. And I insert this is with full back reaction. And of course, what we would like to do is to do binary. So that's still work in progress. And we've managed to evolve some binaries for some time, still not to the end yet, but we're getting there. And this is just a snapshot just to show that you can do it. And this is just a snapshot of a binary with intrinsic spins. They're aligned. So you see the scalar field again. As a scalar field, you see it has one sign on the upper part of the plane and an opposite sign on the lower part. So that breaks parity. And of course, if you choose these black holes to have anti-aligned spins, then you would see the opposite configuration on the other black hole. So it'll be quite interesting to see what is the impact of this explicit parity breaking in the actual waveforms that you get. So that's what we are trying to do. And yeah, just I'm getting near to the end. So let me just quickly summarize and conclude. So this approach of regularization is a constructive method that allows one to formulate the initial value problem for a wide class of higher derivative theories of gravity in a way which is well posed, and it preserves covariance of the theory, and it doesn't require any fine tuning other than just ensuring that the masses of the massive fields that you introduce, masses squared, are positive, but you can always achieve that. Then the higher derivatives of the theory are basically packed into new ghost-like degrees of freedom. But if you choose your initial conditions for these fields such that they're compatible with this expansion in derivatives, then these ghost fields should not be excited during evolution. And in this way, you should be able to construct a consistent solution to the effective field theory. And in fact, one can generalize this to even non-relativistic theories or theories that do not derive from a Lagrangian. And so this procedure is actually more general than what I explained here. So and with that, I encourage those in the audience to sort of prove stability of Minkowski space in one of these higher derivative theories. So that's not known. It would be quite interesting to know. And with this, with this homework for the audience, I will stop and thank you for your attention.